Hi, and welcome back to this video series about probability theory, the logic of science by Jaynes. In the last two videos, we took a little bit of a detour through some of the later material in the book to give the kind of historical and theoretical background of the orthodox methods that Jaynes is kind of writing in response to. So this week we're going to pick things up where we left off in talking about chapter 6 called parameter estimation, elementary parameter estimation. So we've mentioned these ideas a couple of times in the course of doing that review of the orthodox methods, but just to get a little bit more precise about what we mean when we say parameter estimation. When we talk about parameters, what we generally mean by that is kind of any unknown constant or quantity that plays a role somehow in the sampling distribution of the data or probabilities that we're assigning in the course of a problem. Okay, so an example that we've talked about already a couple times before is, let's say in the context of an urn drawing problem, so drawing balls out of an urn with some proportion of different colors, we may think of that proportion as being some kind of unknown quantity. And even though we don't know it, we might be able to kind of compute probabilities based on it. And then the whole question is going to be, all right, in the way that that quantity kind of influences our probability assignments, then given some observed data, what can we say about our posterior probability assignments for that quantity? Okay, so the whole kind of goal of parameter estimation is going to be to work backwards from the data and get some understanding of what probable values this unknown number has based on kind of prior assumptions and the ways that it plays out in the sampling distribution of the data. Okay, so the first and probably the most important thing to understand about parameter estimation then is that it's actually exactly the same thing as multiple hypothesis testing as we kind of saw it play out in chapter 4 of the book. Okay, so the way that that correspondence would work is if we think about, let's say, just calling the hypothesis h theta, giving that name to the hypothesis that the parameter value has or is equal to a particular value theta. Okay, so if we think about this unknown parameter, whatever it is, could have a value theta, and we sort of use that as an indexing variable just to label the hypothesis that it takes that particular value, then I think you can see, if you sort of think about that for a few minutes, that assigning probabilities to these hypotheses in the way that we've done kind of multiple hypothesis testing is exactly the same thing, or corresponds exactly somehow to assigning probabilities to this parameter, or coming up with a probability distribution of the parameter. So they're actually really one and the same thing if we've kind of restricted ourselves to the possibilities that these are all of the hypotheses that we'll consider. Okay, so basically what we're going to do is say, okay, within the confines of some model, we can write down all of the possible parameter values, index them in some way, and then based on data, doing a hypothesis test over that class of hypotheses is exactly the same as assigning a probability distribution to that parameter. Okay, that probability distribution we'll usually refer to with this kind of little p notation. Okay, so this will be p of some value theta, conditional on any kind of information that we come up with in the course of doing the problem, and that's just going to be the probability associated to this hypothesis where the parameter takes that particular value theta. Now this notation actually gets a little bit confusing, and unfortunately Jaynes is a little bit loose about this too, so hopefully in the context of a given problem it'll be kind of clear. But so basically where the confusion comes about is that we kind of think of theta as also being the variable and as being the particular value of the variable at the same time. So we'll talk about probabilities of theta, but what we really mean by that is the probability of whatever parameter we're talking about having a particular value theta, and we just may refer to that parameter by the name theta or n or whatever it is that we're talking about. So occasionally this notation just gets a little bit confusing. We're talking about the variable or a particular value of the variable / index of this hypothesis. Okay, hopefully it'll be clear as we go through the problems, but just to warn you. So doing parameter estimation is exactly the same thing as doing a hypothesis test. This is a little bit different from how you'll normally see it in a standard statistics textbook. And actually, I think it's really the power of the Bayesian method that unites all of these things together into one kind of logical framework. So there's no special techniques for estimating parameters that aren't what you would use for doing hypothesis testing. Basically, then what we're going to be trying to do is a posterior probability assignment for this for these variables, which will usually approach in exactly the same way that we've done hypothesis testing, where we'll say our posterior probability assignment, maybe posterior to some observed data, is our prior, okay, maybe that's just a prior probability based on background information, times a ratio, which is the sampling distribution conditional on that particular value, divided by total probability of the data not conditional on that value. Okay, so this is again just the product rule of probabilities, but written out for this particular kind of notation where we're talking about probabilities of hypotheses of this particular type. Okay, and as usual, the part that we're going to have to focus the most on is this denominator term here, which is the total probability of data not conditional on a particular value of the parameter. And the way that we'll approach that, exactly as we've done before, is to decompose it into a sum or integral over all of the possible other values that the parameter might have, and their probability, their prior probabilities, and their sampling distributions. Okay, so we'll see this played out a couple of times. So basically, our approach to this denominator term should be very reminiscent of what we've done with multiple hypothesis testing, where we decomposed data proposition into multiple possible hypotheses that can explain that data. Okay, so really the material in chapter 6 just consists of a few kind of detailed worked examples of different classes of problems where the parameters have different forms and they influence the data probabilities in different ways, and we make different assumptions about their prior probabilities and come up with a different kind of posterior assignment for the parameter distribution. Okay, so Jaynes does this out in really what I think are three kind of broad classes of problems. And the first is something we've already talked a little bit about, which is taking the urn drawing example and turning it around. Okay, so we'll just kind of think about that. So the idea with urn drawing, remember, is that we assume that we have, let's say, an urn. Draw over here. Okay, something like this. And within that urn, we have some number of balls total, of which, let's say, some number capital R are red. Okay, so we have n total balls, and R of them are red. Already you see a little bit of this notation where these are now the variables, but we're going to talk about particular values of them, which we'll call n and r, but we'll get to that. We then do a sample without replacement, and we assume that we get a sample of little n, of which little r are red in the sample. Okay, so we have capital N and capital R in the urn. We do a sample of size little n, and we get little r of them being red. And the point here is that we actually now imagine that we don't know capital N and capital R. Okay, so the question is going to be, what can we say about the probability of n and r, okay, posterior probability assignment, n and r conditional on our observed data and whatever the background assumptions were that got us to that point. And our data we will think about as just being the observation of the sample. Okay, now this actually seems like it's a little bit more complicated than what we were just talking about, because we have two parameters. We have n and r that we'll think of as both being kind of unknown to us. but actually that's fine. It doesn't affect the logic of the parameter estimation or hypothesis test any. It's just basically to say that we could think about the vector n comma r as our parameter, or we're thinking about the joint distribution of n and r. But we can just as easily estimate both of them based on the data sample. Okay, so how do we do that? Well, first thing we have to think about is what's our data likelihood, our sampling distribution of the data given a particular choice of values for the total number and the number read in the urn. And we saw this already before in chapter 3, but just to remind you, let's write it this way, the probability of the data conditional on a particular configuration of the number of balls in the urn and some subset of them being read, for a sampling without replacement problem, we worked out to be this hypergeometric distribution number. And that, in this case, would be capital R choose R, capital N minus R choose N minus R, divided by capital N choose N. Okay, this is the hypergeometric distribution when you think of it as a function of little r. And if you're looking for a way to remember or understand this formula, I didn't mention this the last time we talked about it, but you can kind of see the different components of it as the number of ways of choosing the various subsets that are represented in the sample. Okay, so we said in the sample we have a total subset of little n, of which little r of them are read. So the number of ways of just getting the subset of the little r read ones out of the population of capital R read ones is this first term. And then the number of ways of getting all the rest of them, say the white ones in the sample, is however many white ones we had in the urn, binomial coefficient with the number in the sample. So that's the number of subsets of that size from that kind of population. And we're assuming that we get one of these and one of these, so the joint number of ways of doing that is the product of those two things. And then the denominator term here is just the number of possible samples. Okay, so it's the number of balls in the urn, choose the number of balls in our sample. So we're basically saying effectively that all of these subsets of size n are equally likely, and the number of ways of getting a subset that's made up of little r red ones and n minus r white ones is this product of these two things. Okay, so that's a way to kind of just conceptualize this hypergeometric distribution thing. Okay, so now the question is, we've got our data probability, that's going to be kind of the numerator term here, and we want to get this posterior probability, which will be what's on the left-hand side. So we have to think about these other two terms here, which are the prior probability and the total probability. Okay, so the prior probability, let's just say we write this out as P n and r given data is going to be prior probability n and r times this ratio, okay, divided by probability of d. This first term here, we can actually break down further as a probability of, let's say, r conditional on n and background information times the probability of just n. Okay, so this is just applying the product rule to this joint probability of the two parameters by saying, well, the way we can get a combination of the two parameters is first picking a value of n and then picking the value of r conditional on that value of n. Okay. Similarly, if we want to attack the denominator term here, basically what we're going to do is decompose that into a sum of all possible pairs of these parameters n and r. Okay, so let's do that here. So we'll say this is maybe the sum over all possible n and r, and I'm going to use prime notations here just to indicate the indexing variable for the sum, whereas n and r are the particular values that we're interested in doing a hypothesis or posterior probability assignment to. Jaynes doesn't do this, but I think it makes it a little bit more clear. So probability of the data, we can write as the sum over all possible parameter values of probability of the data conditional on those parameter values times then the probabilities of those parameter values conditional on background information. Okay, so far so good. The first term here is exactly going to be this hypergeometric distribution thing. So we're just basically saying, well, for any possible choice of n and r, our data probability would be the hypergeometric distribution. So the question is going to be the second term, what's probability of n and r conditional on background information, and that we're just going to attack the same way, right? So we can write this as kind of a big sum, and I'll write it as a double sum actually. Okay, hypergeometric distribution thing we'll leave like this for a second. Then we'll have probability, let's think about r conditional on a value of n, and then the probability of n alone, conditional on background information. Okay, so hopefully you can see how this joint probability of n prime and r prime breaks up into this product rule, first choosing n prime, and then choosing an r prime, number of reds, conditional on that given n prime. Okay, so that thing is just a product rule applied to that, and then we have data probability for whatever that joint combination is we come up with. And we have to take the sum here now over all possible values of r prime and n prime. And let me write that as the sum, let's say, over n prime, and then the sum for r prime we know can only vary between 0 and n prime. Okay, so once we've picked a value of n prime, right? N prime is the number of balls in this urn, this kind of other fictional urn with some total number of balls n prime. R prime is some subset of that, the number of them that's red, so it can only vary between, let's say, 0 and n prime. Okay, so basically this is the full kind of expression for the denominator term here, which is our total probability of the data. And if we have prior probability assignments for n, right, and we have a prior conditional probability assignment for r given any value of n, right, then we'll have all of the ingredients we need to build up this term and to build up the numerator term in the first term here. And what hopefully kind of should start to jump out at you is that this numerator term, the data probability and the prior, so kind of lumping these two things together, is just one of the terms in this master sum over all possible parameter values. Okay, that's going to be a common theme, and we'll come back to that time and again. Okay, so in principle, actually, at this point we're done, right? So we've got our full expression for the posterior probability distribution of n and r as a function of whatever prior assignments we make, and then this data probability thing, which we said is a hypergeometric distribution. So the whole question of the problem is going to be, all right, what are these priors? Right? What kinds of reasonable prior information might we embed in the problem and then translate that into assignments for probabilities of n and r? Okay, so Jaynes mentions a few of these, and you can basically imagine whatever you want. I think the important thing to notice is that there's a very kind of significant term here, which is the conditional probability of the number of reds conditional on the number total. Okay, so in generality, you might think those aren't necessarily related to each other, except for the one being kind of bounded by the other one between 0 and n. But you could imagine kind of background information that would give you some linkage between the two. So maybe someone gives you the urn and they say, okay, I'm not going to tell you how many balls are in it, nor how many of them are red, but I'll tell you at most 5% of them are red. Okay, so somewhere between 0 and 5% of n is the number red. So that would be basically saying r is less than 0.05 times n, right, as a kind of restriction on the prior probabilities. And then if you did the sample and you got, let's say, 10 red balls in the sample, then you would know deductively even that there had to be at least 200 balls in the urn to begin with. Otherwise, you couldn't have gotten 10 of them in the sample, and there only haven't been 5% in the urn. So you can kind of play some games like that, or think about possible connections that would be embedded in the conditional probability, the one that we'll actually spend more time thinking about is actually the one where we assume that n is kind of given. Right? So we're going to assume that this distribution of n prime just basically has a point mass at 1 point, so it's a probability of 1 of being some particular value. And then based on that, we'll think about conditional distributions of R. Okay, so if we took, let's say, the choice where R was uniform. Okay, so let's say we have a given value of n. Okay, so all of our background information is going to be conditional on n. Let's imagine that R is uniformly distributed between 0 and n. And what we mean by that is that all of the values from 0 up to n are equally likely. Well, what that means in terms of its probability assignments is that the probability of R conditional on n and I is just going to be 1 over the number of possible values here, which is n plus 1, okay, because we're including both the endpoints. And this is going to be true for every R between 0 and n. Okay, so again, here we're thinking about R as both the variable and the kind of values of the variable as we go from 0 to n. Okay, so if you take that probability assignment, right, which gives you everything you now need to know for this term and for this term, okay, probability of n, this is just going to be 1 for the particular value of n, same here. And the data probability we already know is the hypergeometric thing. If you put those into this expression, you get a little bit of nice cancellation. So you get kind of this 1 over n plus 1 value appears both here and here in the denominator, so they're going to cancel each other. And the hypergeometric distribution kind of looks the same. So in the end, what you get to, I won't do all the steps, but what we get to in the end is a posterior probability assignment. Let's write it this way. For R given the data, the known value of n, and all the background information, which just basically looks like the hypergeometric distribution. So it's R, choose R, capital R, choose little r. Capital N minus capital R, choose little n minus little r, then divided by capital N plus 1, choose little n plus 1. Okay, put a box around that. So that's the posterior probability assignment for the number of reds, conditional on our sample information, and assuming that we have basically a known value of n, but within that, no extra knowledge about the number of reds. Okay, so we're kind of indifferent to the number of reds given the value of n. And what I think you should take away from this is that this looks a lot like this expression. Okay, in fact, the numerator term is identical to this data likelihood as a function of n and r. And the only thing that's different is the denominator, where basically we have a different kind of scaling factor. So this number doesn't depend on r, but it is a slightly adjusted scaling factor of this data likelihood. Okay, so you might say this is kind of the hypergeometric distribution, but where we think now as we think of the variable as being the number capital R instead of being the number little r. Okay, so instead of kind of summing horizontally across the table, we're thinking about going vertically, right, for different values of R. And this is going to be a general pattern that we'll see, I think, a couple more times, where our posterior probability assignment on a uniform prior assumption is just proportional to our data likelihood. Okay, we actually saw this once before already, but that's going to be a general theme. Okay, so actually this is, again, kind of the end of the problem in some sense. We've taken our data information and we've turned it into a full posterior probability assignment for the one unknown parameter. Okay, but now actually the question might be, all right, let's say that instead of talking about a probability distribution, we actually want to know, what's the one value we would pick if we had to pick one. Okay, so this is kind of something that's a little bit particular to parameter estimation problems as opposed to general multiple hypothesis testing problems, is that often it's the case that for some downstream problem or calculation we're doing, we actually have to pick just one particular value of this parameter that we're going to use as a kind of estimate of the unknown quantity. So we want to know, all right, what's the best value to pick out of all the possible values given this distribution? And again, this is limited to just the possible numbers 0 up to n. All right, well, one thing you might imagine doing is just taking the value out of this distribution that's the most probable. Okay, that would be kind of a perfectly fine estimator to use, and it would just basically mean finding the value of capital R that maximizes this expression. And if you did that, you would end up with the number capital N plus 1 times little r over little n. Okay, so I'll skip all the intermediate steps, but that's basically where you get to if you look at maximizing this quantity as a function of capital R. We've actually seen this a little bit before. What this means is that kind of the most probable distribution in the urn kind of matches fairly closely with the distribution in our sample. Okay, so if you think about doing the sample and looking at the sample ratio of reds to totals, what we're saying here is that the urn ratio, kind of reds to totals in the urn, is pretty much at its most probable value when it matches the in-sample ratio of reds to total. And the only difference is this n plus 1 term instead of capital N. All right, but it's basically the in-sample ratio times the number in the urn is the number that you would think is most probably the number of reds in the urn. Okay, that's one thing you could do. Another possible estimator that you could extract from this would be to take the mean. Okay, and we haven't talked too much in detail about what this means, although we have used it a couple of times. Basically, whenever we talk about the mean, which we can either write as expected value notation, so capital E, or just E of R, say over this conditional distribution, or we might write it as bracket notation, capital R. All we ever mean by that is the weighted average of the values of R weighted by the probabilities in its distribution. Okay, so what that would amount to is taking the sum, okay, over all the values of R from 0 to n of the value R times its probability, conditional on all this information in the posterior probability assignment. Okay, so that's just what expected value is, or what an average of a quantity with a probability distribution is. And if you did that for this distribution, okay, again, things get a little bit hairy and you have to kind of work with these binomial coefficients, expand them out, but once you do that and take that sum, what you end up getting actually is kind of a nice expression, which is just little r plus 1. Let me write it this way. It's capital N plus 2, little r plus 1, divided by little n plus 2. Okay, so that seems a little bit strange, but actually it becomes a little bit nicer if you turn that into the expected fraction remaining in the urn. So if you take f as the fraction now of remaining balls in the urn after you've drawn some number in your sample, that's a random variable, okay, so it has a probability distribution. Its expected value is just the expected value of the number of reds in the urn minus the r that you took out divided by the total that was in there originally minus the little n that you took out. Okay, so remember r is what started in the urn and we took out little r of them. And if you do that expression, plug that in, for expected value of r, what you get out in the end is actually something quite nice. It's little r plus 1 divided by little n plus 2. Okay, so again, I won't do all the algebra there, but I trust that you can kind of work that out on your own time. This is the mean value, okay, of the distribution of the remaining fraction of red balls in the urn after doing the sample, assuming that we had a uniform prior, okay, on the number of red balls in the urn originally. It also happens to work out to be, and again, you can kind of think this through, it happens to work out to be the probability of getting a red ball on the next draw. Okay, so this is the probability of, in our previous notation, red on the, let's say, n plus first draw, conditional on this data and these background assumptions about number of balls, etc. So basically, what that's saying is that kind of the average fraction over its frequency is also the probability of getting a red ball on the next draw, and that comes about because this probability is sort of linear, and you can write it out over all the possible values of r, and then it kind of comes out of the sum. Okay, I'll leave that for you. This result that you get r plus 1 over n plus 2 has a name. It's actually called Laplace's rule of succession. Laplace's rule of succession, which Laplace first came up with, I think, in connection with what's called the sunrise problem, which is kind of a thought experiment of thinking about, in a kind of Bayesian framework, what probability would you assign to the event that the sun is going to come up tomorrow, given that you've seen it come up every day of your life for some string of days. And basically what Laplace's argument was is that if you first of all think of that as being a kind of urn drawing problem each day with a ignorance prior or a uniform initial probability assignment to that single probability, okay, and you do that some number of times, little r times and little n times, and you get little r successes, then your next probability assignment for the next event is r plus 1 over n plus 2. It's a little bit funny that there's a plus 1 and a plus 2 here, and Jaynes talks about this a bit in the chapter, and actually trying to find a pre-prior distribution that would get you to just r and n, which is kind of more what you'd think it would be. We'll come back to that when we talk about the Jeffreys prior later. But a lot of people basically over the years have criticized Laplace for making that argument because they think that's a ridiculous kind of thing to say, that you'd have a less than 1 probability for the sun coming up tomorrow based on having observed it come up every day. But essentially they've just all kind of misunderstood his argument. So he was basically saying that's the probability you get if you start from a position of total ignorance about the probabilities of the various events, which is obviously not the case when we think about things like the sun coming up. Okay, so it's an idealized thought experiment that gets you to this nice result, but it's not really what would apply in a particular real-world problem. Okay, so that's a couple of maybe possible choices we could make for the value of this estimator that we might choose as a kind of proxy or stand-in for the unknown parameter r. Okay, so Jaynes talks about this a little bit, that in general, when we do a kind of posterior probability assignment, there are some nice kind of choices for this single estimator. If we have to pick one value, there are kind of some canonical reasons why you might choose one summary value or another. What he talks about is, let's say for a continuous parameter, okay, so what would the continuous version of this be? Let's say for a parameter alpha, okay, with a probability distribution, let's say p of alpha, and this is based on whatever information got us to the point of assigning its probability distribution. The kinds of choices you might make, well, you could pick the kind of mode of the distribution, meaning just the peak value of the probability function, Or, and what's more commonly the case, is that you'll pick the average value, which for a continuous number you have to define in terms of an integral. Okay, so I'll just kind of write that out here. It's the same kind of integral as we had a sum when we do the expected value computation. So it's going to be the integral over the probability distribution of alpha times probabilities of alpha, now integrated with respect to alpha over whatever domain alpha lives in. And the nice thing about this that Jaynes kind of works through that might suggest it as a good estimator is that it actually minimizes what's called the mean squared error. Again, something we talked about a bit last time. It minimizes the mean squared error over the probability distribution. Okay, what that means is that if we looked at, let's say, the parameter minus some number, let's call it alpha star squared, okay, and just thought about the average of that quantity for any particular choice of alpha star over this same probability distribution, okay, so that's kind of defined to be the same thing, d alpha, that quantity is minimized when we take alpha star to be the average value of alpha. Okay, so in some sense this is kind of the center of mass of the distribution in that it minimizes the overall squared differences between alpha values and this particular constant. And that's just kind of a nice property to have, and Jaynes gives a little proof of this. I don't think it's too essential to work through, but it's interesting to think about. You might, if you were, let's say, more inclined to use absolute value differences instead of squared differences, okay, as was the case when sort of Laplace and others first came up with this, what you'd actually end up with is instead of the mean value, you'd get the median. Okay, so it turns out that the median of the distribution minimizes the error if you write it in absolute value terms instead of if you write it in squared difference terms. Okay, again, just kind of nice properties that you might look for if you had to pick a single value out of a distribution as your kind of proxy for this unknown parameter that you have, many possible values with associated probabilities to. Okay, other things you might care about, and again that Jaynes works through in this particular problem, but I won't repeat all the calculations for, is, so I just erased it, but we have the probability distribution over all the values that R can take, and we saw, maybe how we pick one value. You might want to know, all right, well, how concentrated is that distribution? How much confidence do I have in R living in a particular region of that distribution? Not just what's the one value I would pick. And the way that you typically summarize that is what's called the variance, okay, again, of the distribution, which is a very similar looking thing to what we just wrote. It actually works out to be the average of the squares minus the square of the averages, okay, where again, here we're talking about the average over the probability distribution assignment for R, for this unknown parameter. Okay, so that's, if you like, a measure of kind of how spread out the distribution is of R, and the smaller it is, the more tightly concentrated we have that probability assignment being, and the more kind of accurate we would claim this estimate to be. Okay. Other things you could look at may be percentiles of the distribution. You might say, okay, instead of the variance, I want to know just what's the 25th percentile or the 75th percentile or any other quantity you want. And basically the point here is that as Bayesians, we have all of these things available to us. Right? We have a full probability distribution assignment, so we can pick out from that really any summary number we want or any kind of interval estimate we want or range that we want to summarize our state of knowledge about this unknown parameter. Okay. All right, so that's one kind of broad class of examples where we've taken this one kind of urn drawing situation and turned it around to think about parameters of the urn as being unknown. The second broad class of examples that Jaynes talks about in this chapter are what I would call the source-detector problem. Source-detector. which has basically the same common setup each time, where what we assume is that there's some source of objects of a particular type or entities of some characteristic that we're interested in. Some source is producing these according to some process that is a little bit unknown to us. Okay, we'll see what that means. But then what happens is that we pass them through some kind of detector that only notices them each with some probability. Okay, so we have a source which gives some number n, which is the number in existence, right? We then put all of these objects, whatever they are, through a detector. And what comes out of that detector is a number c, which is the number counted. Okay, and our assumption in setting up the problem is that each object that goes through this detector has independently a probability of little phi of being detected by the counter. Okay, so this could be something like, in Jaynes' examples, maybe n is the number of people in the population who contract a certain disease or have a certain disease each year, but we only kind of notice them if they die from the disease and we perform an autopsy. Okay, so the number counted is basically whatever subset of the people who have the disease end up dying from it and getting detected. Or it might be like the number of mosquitoes that breed in a population of some swamp nearby, and then some of them fly over to where we are and get caught in mosquito traps and become our kind of number counted. Or the kind of particular example that I think Jaynes was interested in was where we have maybe a source of radioactive particles, sort of generating particles according to some process, and they pass through some detector, but they only sometimes get noticed by the detector or get counted in the final count. Okay, so basically the issue here, what's going to make this kind of an interesting problem to think about, is that this number counted is going to be what we assume we have in our data, right? But that number is kind of randomly, if you like, dependent on some number that we don't know. Okay, so n in this case is going to be our parameter for the problem, and we're going to have maybe some probability assignments for n based on whatever this source process is. Okay, but to start with, we can write down at least what our data probability is for the number counted conditional on a particular value of n. Okay, so if we think about assuming that there were n things in existence, and we know the efficiency, if you like, of the counter, so we know this number phi, it's given to us as a property of the counter somehow, the probability of getting c out of n is just going to be a binomial coefficient with this success probability. Okay, so it's going to be the binomial coefficient n choose c. We have phi to the cth power, and then we have 1 minus phi to the n minus c. Okay, so it's like our sampling with replacement problem, where each thing has some probability of being included in the sample, and we have to think about the number of ways of choosing that subset of little c out of the set of size little n. Okay, so again, what we're trying to get to is a probability assignment for this parameter n based on our observed data. We now have our data sampling distribution, so we have to think about what prior will we assign to this parameter n based on just background information. Okay, and we'll include in the background information that we know the counter efficiency, although it's not going to matter too much. Okay, what kinds of priors might we use? Well, Jaynes mentions a couple of them. One general class of distributions that's going to be very useful for problems like this might be where we assume that n comes about from some binomial distribution generation process. Okay, so binomial distribution with, let's say, capital N source objects of some kind, whatever those are defined to be, and each of them have some independent probability of producing an entity, a person with a disease, or a radioactive particle, or whatever it is, a particle from radioactive decay, where this number n is very large and this number r is very small. Okay, so the assumption is basically each one has a very small probability of producing one of these things, but we have a large number of them all acting simultaneously and independently from each other. So in principle, that's a binomial distribution then of the number that we get. But actually, for this case where we have a large number of things and a small probability of succeeding on each one of them, and we assume that, let's say, n times r is of a reasonable scale, some number called little s, this binomial distribution is going to be about the same, or well approximated by what's called a Poisson distribution, with a parameter little s, where little s is this product. Okay, so the Poisson distribution is a very useful kind of distribution to have at our disposal. It's a distribution on the integers with this one parameter s, and what it means is that the probability of getting n of them, say conditional on s, is e to the minus s times s to the n over n factorial. Okay, so that's just the Poisson distribution as a function of little n. This is sometimes called the law of small numbers. Okay, so people have been using the Poisson distribution as an approximation for the binomial for a long time, and it happens that that approximation is very good in this kind of limiting case where the number of trials we're doing is a large number, but the success probability for each trial is very small, and the product of those two things then becomes this kind of key parameter in the Poisson distribution. This has the property that the mean, so right here, the mean of n, the mean of n over this distribution is actually this number s. Okay, so the way to think about this, again, if you want some intuition, is that s is kind of the average number produced, or the source strength, average number of things produced per each unit time, okay, where we have this number of things acting simultaneously, each with a small probability. Okay, that's the Poisson distribution. Has a nice kind of form, and we can calculate various properties of it. So that might be, for a general class of problems, a kind of reasonable prior probability assignment to make for probabilities of n, where we now assume that this source strength is something that we know. It's kind of a given parameter. Okay. So how then do we go about doing the parameter estimation? Well, just as before, what we really care about is the total probability of the data, now not conditional on a particular parameter value, n, but we'll write that just as a sum, okay, the same way we did before, over all possible values of n, where we take the data probability conditional on that value times the probability of n prime. So it's just basically decomposing our data probability into all of the possible parameter values, probabilities of n prime, times conditional probability of the data given that n prime. Okay, and writing the sum over all possible n prime. Okay, now these are things that we already know how to do, right? So we have our data probability is this binomial coefficient thing here. Okay, so I won't rewrite it, but we've got the form of it. Our prior probability for n, okay, I didn't write the s, but it's in the background information is s. Our prior probability for n is this Poisson distribution. Okay, so we could calculate that thing out. Given all that, we have our total probability of getting c counts, right? And that, again, gives us everything we need to know. So we could write the posterior probability for n, now given an observation of C counts, as prior probability for that particular n times data probability for that particular n divided by this sum, which is probability of the count not conditional on the value n. Okay, so there's s's in these background information. Okay, basically we're done. We have all the ingredients we need for each of these various components. I won't write out all the arithmetic because it gets a little bit hairy with adding up these binomial coefficients times Poisson terms, but we have, in principle, everything we need. What actually comes out of this, which is quite interesting, is that once you do all of this, what you find is that the number left uncounted, okay, so the number of uncounted particles or objects of whatever type, which is the number that exists minus the number that you counted, actually works out to have a Poisson distribution with a parameter which is the source strength times 1 minus the counter efficiency. Okay, that's what I want to write. Okay, S times 1 minus phi, where phi was the efficiency of the counter that's picking out the number C out of the number n. Okay, it's a little bit of a surprising result. It actually comes from a property of the Poisson distribution, I think called Poisson thinning or something like that. What this means, actually, is that the average of the distribution for n is just C plus the average of this Poisson distribution, so however many we counted, plus the mean of this Poisson distribution for the number that remain uncounted, which is going to be C plus just this parameter in the Poisson distribution. Okay, S times 1 minus phi. Okay. I think that's quite interesting. That's the average of our posterior probability assignment for the number in existence, posterior to having observed we got C of them, but based on this Poisson model for how many existed to begin with. And what is quite interesting about that, I think, is that if you think about now how this varies as a function of C, right? So if you do this experiment a couple of times, you get different data values, you get different counts. How does your estimate of n change? It basically just changes by the same amount, right? So if C goes up by 1, your posterior estimate of n goes up by 1 if you're using the mean of that distribution. Similarly, if it goes down by 1, n goes down by 1. It's a little bit, I think, counterintuitive because you might think what we should do is, well, we got C in the count and we know the counter efficiency is this number phi, so we might just guess a value of n, or an estimator of n, that is the number that we counted divided by the efficiency, kind of scaled up by the appropriate quantity, whatever it was. So if we were to, let's say, put some numbers on this thing, let's say that we said we had a source strength of 100 particles per unit time, however we're defining it, and we counted with a counter that had an efficiency of, let's say, 10%. So 10% of the particles on average get through, but it's a kind of unknown quantity based on this binomial distribution thing. If we then counted, let's say, 15 of them, right? So this is our source strength, but we know n can vary around that kind of mean value. We know that we get on average 10% of them, so we have this kind of compound randomization problem. And for a particular experiment, we got 15 of them. This value that we would use from this posterior probability distribution coming from the Poisson model would be, let's see, 15 plus 100 times 9, or times 0.9, so 90 plus 15, we'd get an estimated value of 105, right? Whereas this thing would lead us to just 15 divided by 10%, so 150. So quite a large difference between the two ways of going about things, basically just coming from the fact that we have very strong prior information here embedded in this Poisson distribution thing. Okay, so if you like, you can see this as saying any fluctuation we get in our number counted, right, has more to do with the counting operation than it does with the generation operation, because we have a lot of very strong information about the distribution of things being generated. Whereas just in a naive approach, you might say, well, whatever the fluctuation is, it's all in the number that exists, because we just take whatever number we count and scale it up by the counter efficiency. Okay, so you can think about how that will actually play out in detecting the incidence rate year to year of, let's say, a disease where very few people die from it. So we have a very low efficiency number here. And that would mean basically that these fluctuations in the count don't cause much of a fluctuation in our posterior estimate, relatively speaking. Okay, so Jaynes talks about that a little bit, but just I think it's important to highlight that this prior information is playing a large role. And what you could imagine doing is saying, okay, let's take a different tack, which would be what would happen if we didn't have that Poisson model. We didn't like that kind of prior information. Instead, we thought about n as just being a uniformly distributed quantity on, let's say, the range from 0 to n minus 1 for some large n. Okay, so we can get any number of particles between 0 and n. So what that means is that our prior assignment might be like 1 over n. This is the reason for the n minus 1, is that now we have n total for 0 less than n less than or equal to n less than n. What would that shake out to be? Well, basically, we've already kind of done this problem a couple of times, where with a uniform prior, right, we know that what we get in the end for our posterior distribution is just the data likelihood. Okay, so this number is just going to drop out. This number is going to be a sum over a bunch of things that don't depend on little n, and so it's just going to be proportional to the data likelihood for that particular value of n. And what it plays out to be is this. So the posterior probability assignment for n given c and this alternate state of information, where we're assuming n is uniform, or we're assigning it the uniform distribution, is just the data likelihood binomial distribution thing, but with an extra factor of phi thrown into it. Okay, so instead of phi to the c, we have phi to the c plus 1, and that extra power of phi comes about from the denominator term here, which works out to be 1 over phi. Okay, so that's something to kind of work through on your own, but the lesson is that it's just proportional to the data likelihood function, which is the binomial distribution that we see in the numerator there. Okay, now what's different about that? Well, in particular, we know what its mean and peak value and everything are. The average value of this alternate distribution works out to be something like c plus 1 minus phi over phi. Okay, and it has a peak value, I think exactly at or maybe within one value of the number c over phi. So basically, this is what we would have guessed in this kind of naive version, right? So, to within a small amount, c plus 1 minus phi, that's about c divided by phi, either in the mean or in the mode, kind of agrees with our naive guess of just taking the number counted and scaling it up by the counter efficiency. And so in essence, what that's saying is that this approach corresponded to a prior state of information where we made as minimal an assumption as possible on n as we could. We assumed it's uniform on some very large number, capital N, or 0 to capital N. Now what is actually kind of, I've skipped over here, but is interesting to think about is that there's no capital N in this final expression. Right? We made an assumption involving capital N's here. It's not here. The reason for that is that actually somewhere along the line, we've made an approximation where we've taken the limit where capital N goes to infinity. Okay, so Jaynes does a comparison here where you can actually see for particular finite values of n, how much difference does it make in terms of your final, say, mean or peak value assignment. And it's very, very minimal for the kind of numbers we're talking about here. Okay, so basically the difference between an n of, I think, 4 or 500 ends up playing, making less of a difference than the 4th or 5th decimal place in this posterior mean assignment. But it's a little bit tricky because we do need a finite value of n to assign a proper uniform distribution on this range from 0 to n. Okay, and so you can always think that in a real problem, we would know that this thing is finite because we would know that the number of people getting a disease is less than the number of people in the world, or the number of number of particles being generated is less than the number of particles in the universe, or less than whatever it would take to kind of vaporize the laboratory that we're working in. Okay, so you can always put some kind of finite bound on it. And the point is that the problem is finite, right? We'll assume that that bound exists. In the end, we might make an approximation where we let that number go to infinity just to make the math work a little bit nicer. Okay, the formulas become a little bit simpler when you can take, infinite sums or integrals or whatever it is. Okay, so that's something that Jaynes goes through in detail. But in the end, in this case, when you make that approximation, it's a very good approximation, at least on the scale of numbers that we're talking about here. Okay. The other thing you could imagine doing, if you, let's say you like this Poisson thing, but you didn't like the idea of it being just kind of given to you, is that you could imagine, again, that n has a Poisson distribution, Poisson sampling distribution with some parameter, but where s is also unknown. Okay, so s is an unknown parameter. Okay, so what would that look like? Well, basically now the issue is, okay, we want to play the same game of doing a posterior probability assignment for s based on some observation of the number of counted entities. So we'd say, okay, posterior probability assignment for s, conditional on our data, which is the count, would be whatever prior distribution assignment we made times data probabilities for that s divided by total data probability. Okay, now we have kind of an annoying thing standing in the way, which is that we don't actually know this data probability for c given s. We just know the probability of the data given n, and we know the probability of n given s. Right, so we have this kind of, again, two-stage logical diagram, or a chain of logic where s is unknown. S then influences our distribution of n, right, which is an unknown parameter in assigning the distribution of c. Okay, so you might think, all right, this is really going to make our lives difficult, but actually that's not a problem at all for the Bayesian method. All we basically have to do is take a sum or an integral or whatever it is over all possible values of n. Okay, so we'll get, I think, back to this maybe in some later examples. But when this happens, what we say is that in this instance, n is what's called a nuisance parameter. Because it's kind of getting in the way of our connection between the parameter we actually care about, the source strength that we're trying to estimate, and the parameter or the data, which is what we're going to observe. But in the Bayesian program, it's very easy to handle nuisance parameters because all we have to do is integrate them out. So let's say that we wanted to know the data probability of c conditional on s, this numerator term here. Well, what we would do is say, all right, we'll take the sum over now all n values of the probability of the data conditional on n, right? Conditional on s, conditional on n and s, si, times the probability of S. Right, so it's just basically saying, what ways can we get a count of C given a source strength of S? Well, sorry, I wrote this wrong. It's the probability of getting C given N times the probability of getting N given S. That's what I meant to write. Okay. So you take that sum over all possible N values, and you get this kind of two-stage logical leap. Okay, hopefully that makes sense. So we go from S to N, any possible value of N, and then once we're given N and S, we go from there to a possible value of C. Okay, this thing we know is the binomial distribution. Okay, we saw that before. This thing again is Poisson. We made that assumption that given a source strength, the count or the number in existence is a Poisson distribution. So we just take that sum. Similarly, if we wanted, let's say, the total probability, not conditional on a particular S value, okay, exactly as we've kind of done before, all we have to do is think about, all right, this is what it is for a particular S value. Now, let's just integrate that thing. Let me use S prime here, just to indicate integration variable. Integrating against the probability distribution of S, okay, over whatever range it lives in. Okay, so the example that Jaynes does out is where we might say, all right, we're thinking of this source strength as being some unknown quantity. Maybe we assume that this is uniform. Okay, and what that means is that it is maybe uniform on some interval, 0 to S0. So its probability assignment is just 1 over S0. Okay, that's the uniform continuous distribution on an interval. For each one of those values, then, we can take this sum over n, right, conditional on that source strength, and find the now conditional probability of getting some count, getting the count C, right? And then we're going to take whatever that thing is, basically each single term like this, and integrate over this whole distribution of S. Okay, so it may get to be kind of a messy problem. Right? There may be a lot going on there, but we actually have, in all of these probability assignments, we have all of the ingredients we need to do that through to its conclusion. Okay, so that'll be our total data probability. We've got the numerator term, which is kind of the single probability for that parameter value, and our prior probability might be the uniform thing that we said over there. Typically those might cancel for a uniform probability, and we'll end up with some posterior probability assignment for S, given an observed count of C. Okay, so again, I won't do this out, but you can see, I think, at least in principle, how you would get there. Right? Now, algebra may get a little bit tricky, but you've got kind of the tools to get you there. So this is what's called the nuisance parameter. We're going to see this probably a few more times, where basically the Bayesian approach to handling nuisance parameters is just to assign them some probabilities and then integrate or sum over their distributions. There's no problem at all. For orthodox statistics, this is a huge problem, and they can only really kind of work their way around it in one or two kind of particular setups where there's nice statistics they can use, and we'll see some of that again, I think, probably later on. Okay, so that's kind of one game you can play. Another thing you could do, which I think is quite interesting, is to then compare this regime with this other regime where we assume some kind of fixed source with an unknown source strength. Okay, so Jaynes talks about this as being, maybe two scientists are observing these experiments iterated multiple times, and maybe let's say person A just thinks that each experiment is independent and treats the number in existence as a uniformly distributed variable with some kind of maximum value. And so his probability kind of diagrams, or the kind of flow of his logic, is always going to look like some value of n1, then gives you some value of C, and then some value maybe the next time around gives you some value of C2, etc. Okay, and each time we get a count, his posterior assignment for the kind of number of entities in existence is just going to be this, maybe this naive thing. Person B, let's say, who knows that these counts are coming from a radioactive source with some fixed strength, but doesn't know what it is, but maybe it has a probability assignment for it that, let's say, is the uniform thing, so goes through this kind of uniform times binomial times Poisson chain of argument here, we'll basically be thinking along the lines of, well, there's S that gives me my N1, right, number that existed for the first experiment that I counted with C1, and then maybe gives me, there's an N2 that becomes C2 when I count it, or an N3 that dictates my count the third time, etc. Okay, so it might happen that based on different prior information about what's causing the variety of results in these experiments, this person and this person end up with kind of different inferential programs or different chains of logic. But what is actually very interesting to think about is how person B would update their probability assignment for N1 after observing the second count. Okay, so maybe this experiment happens first and we go through this kind of program and we get, okay, C1, we work backwards to S. Okay, so we can go kind of that way. Then we get another experiment, C2, right? Or another data result, C2. Because of this chain of logic that allows us to go backwards from C2 to the source strength, sort of updated posterior assignment for the source strength, we can actually then go all the way back and update our assignment for what N1 was. Okay, so Jaynes kind of works that out, but it's an interesting example, I think, in how results of different experiments might actually inform previously unknown values just based on the existence of some common cause or common logical influence of the different experiments. And the Bayesian line of reasoning is going to be the same each time. It's just basically taking the conditional likelihood of the data and using the conditional probability assignments, etc., to work backwards to whatever's unknown, and then you could go forwards one step and say, okay, based on this distribution, what's my distribution of N1 and N2 and N3 and etc. Okay. So again, I won't run all that out because it gets kind of ugly, but logically, I think there's a lot going on there. It's very interesting. All right. So the last class of examples then that Jaynes talks about, and I wanted to go through a little bit, is what he calls the rectangular distribution, or rectangular sampling distribution. Rectangular sampling distribution problems, or the so-called taxicab problem. Okay, so the setup for this problem basically goes like this. So you imagine that you are traveling on a train and you fall asleep and you wake up somewhere, you don't really know where, in some strange town you've never been to before, and you look out the window of the train and you see a single taxi cab with a number on it that is 27. Okay, so it's cab number 27, it's the only thing there. Okay, and let's say that you know, because of your knowledge of how cabs work, that these taxis are numbered sequentially starting from 1, okay, to some maximum number for that town, but you don't know what that is. Okay, so n is the number of cabs in the town. And the question is, all right, based on this single observation of one of them, what is your guess as to the value of this parameter? Okay, what would be your kind of estimate, or what could you say about the number of taxis in a town based on the fact that you observed one and it was the number 27? Okay, so if you think about different kind of intuitive guesses you might make, well, you might think, deductively, I know it's got to be at least 27 because I assume that they're numbered sequentially starting from 1. Right? So I can conclude that it has to be at least 27. So maybe the value I should pick is 27. But that kind of seems not quite right, because that would be saying, well, I looked out the window and I just happened to see the maximum numbered taxi cab in the town, right? The one that got numbered last. Seems kind of improbable. Similarly, if you kind of pushed it the other way and said, okay, maybe my assumption is that there are 1 million cabs in the town, right? Or something like 1 million of them. What are the chances that I would look out the window and see one of the first 27? Right? That's a very kind of unlikely event. It would be like, seeing one of the first cabs created on this massive assembly line or whatever produce these taxis with these numbers going from 1 to 1 million. Okay, so that kind of seems wrong too. So basically, using some intuition, you might think, well, maybe my guess would be somewhere around twice what I saw, so that this number is somewhere in the middle. Okay, so basically, that's the kind of place that most people ultimately get to when they reason intuitively about this problem. But actually getting this in some kind of rigorous way is very difficult, or at least attacking this problem and breaking it down is difficult without this kind of Bayesian logical reasoning. Okay, so this problem has a kind of long and famous history, and is often thought of as being kind of a problem of great difficulty for the orthodox statistical program, because it doesn't really have the right apparatus to deal with it. Okay, so if you just talk about this in terms of sampling distributions, you kind of can't get to a reasonable number. It's otherwise known, you might see it elsewhere, as called the German tank problem. Okay, and the reason it's called the German tank problem is that it came up in a very real way during World War II, when the Allies, in the days leading up to the invasion of Normandy, D-Day, they desperately wanted to know how many tanks there were in the German army, particularly in northern France, and they had very limited and sketchy intelligence information about the German production capabilities at the time. So they basically didn't know how many tanks the German factories were producing, but they really wanted to get a good estimate for how many there might be of a particular type in a particular location at that time. So basically how many were coming off the assembly line each month. So they didn't have much detailed information about the production capabilities, but what they did have was serial numbers for some parts of the tanks that they had captured or found after the tanks were destroyed during the war. Okay, so they had these kind of remnants of these older tanks that had been destroyed, and they could look at the different parts of it and look at the serial numbers in the tanks. And they knew some things about how the German factories were producing these serial numbers, so they could make assumptions about them being kind of sequentially ordered from some starting point. And they wanted to work backwards from the numbers that they did observe to some estimate of the total number that actually were produced in that month or in that period of time. Okay, so this is a real problem, very similar to this. And actually what it kind of just amounts to is generalizing this a little bit, where we, instead of having just one observation, we make multiple observations. Okay, so the basic setup of this, German tank problem, we're going to generalize this to a continuous distribution, although the discrete one is it follows very similarly. The basic idea is that we're going to have n independent observations. Let's call them x1 through xn. These are independent. And we're assuming that they are uniform on some interval. Okay, so they are sampled according to the uniform distribution from, let's say, 0 to alpha independently. And what that means is that the probability of each one of them is just 1 over alpha, where it's allowed to range between 0 and this maximum value alpha. Okay, so our data is going to be the assumption that we saw n of them, and they had these different values. So our data probability actually then, conditional on alpha, and all this background information, is just this number n times. Okay, where each observation has this probability 1 over alpha. This is, the reason it's 1 over alpha here is that it has to scale the distribution to integrate to 1 over the interval from 0 to alpha. Okay, that's probability of each one of them. We're assuming they're independent, so they just power up n times. Okay, that's our data probability. So the question now is, all right, given that data, what can we say about alpha? Right, what can we say about this maximum number, which would be like the number of cabs produced or the number of German tanks? All right. As per usual, right, we have to think about what is our prior. Right, so our prior probability for alpha will have to be something in order for the Bayesian program to go through. And what we'll try to do is say, okay, maybe we'll assume something very minimal. Right? We want to make as kind of a small imposition on the problem as we can. So we'll assume that we are kind of ignorant of alpha to the degree of, let's say alpha has a uniform distribution between two numbers, which we'll call alpha 0, 0. Okay, the 0, 0, we'll see why in a minute. 0, 0 to alpha 1. So some maximum number and some minimum number. Okay, and we'll just think about these as being like a big range of numbers we don't have much knowledge of, but we have to pick some endpoints in order for the distribution to work out. And what that means is that our prior probability assignment, being the uniform distribution, is just 1 over now the width of this interval. Okay, that's the uniform distribution on that interval. Okay, so we want to get to a posterior probability assignment for alpha conditional on the data. So we have our prior, we have our data sampling distribution here. We have to think about our total probability of the data, okay, which is going to be probability of D, now not conditional on a particular value of alpha. But the way we'll get that is by integrating over all possible values of alpha. Let's call it alpha prime. Now this probability distribution for alpha prime, d alpha. Okay, and that the range of that is going to go from its minimum value to its maximum value. Okay. Now, one thing to notice here, and this is why we have to use this double zero and where this gets a little bit tricky, is that for some range of these alpha values, the data might actually be impossible. Okay, so if you then want to think about this graphically, what we're basically doing is saying, okay, first we pick an alpha value between, let's say, two numbers, alpha 0 and alpha 1. And once that's given, we now sample some x values that are uniformly distributed. Okay, so this is alpha 1, this is alpha 0, 0. Our x values might be in here. Okay, or it might be that sometimes we see an x value that's kind of up here. Okay, so given an alpha value, we sample x's. If we saw an x value that's up here, then we know kind of deductively that we could rule out all of the alpha values less than that. Okay, so we know that we have to be at the very minimum somewhere to the right of that value xi for our value alpha, which remember is supposed to be the maximum possible value we could get. Okay, so alpha is like the number of cabs in existence. If we saw some cab numbered 100, then we have to know at least that that maximum number is greater than 100. Now that's actually already taken care of here, so you don't need to worry about it too much. But where it plays out here in this expression is that when we integrate over all of these alpha values, right, depending on what the data is, depending on what the xi values are that we actually observed, we might get a data probability that could be 0. Right? So in this case, let's say if we had an alpha prime value in here, and we're thinking about this data probability for a number that's greater than it, or that includes a number that's greater than it, that data probability would be 0. Okay, but it's not a big deal. So anyway, that ends up being then an integral only over a kind of subregion of this, where we'll go from alpha 0 to alpha 1, this data probability, say alpha prime to the n, times this distribution for alpha, which is alpha 1 minus alpha 0, 0, d alpha prime, okay, where we actually only integrate from the maximum possible, or sorry, from the minimum possible value of alpha. So basically from the data maximum or from the starting point if we could get there. Okay, so this is going to be, let me write it this way. Alpha 0 is going to be the maximum of our data numbers and this starting guess alpha 0, 0 if all of these happen to be less than it. Okay, so all right, that's fine. So that's just basically the lower limit of our region of integration once we account for the fact that some of these data probabilities are going to be 0. We can do that integral out. Okay, we won't actually do it out, but pretty tractable integral to handle. Okay, and if we do that, what we'll get to in the end is that our posterior probability assignment for alpha, given the data, it's going to have this term in it. Will come out of the integral and actually cancel with the prior probability, just as we'd expect. And it's going to be basically our data likelihood, 1 over alpha to the nth power, divided by this integral from alpha 0 to alpha 1, the same thing, 1 over, let's say, alpha prime to the n d alpha prime. Okay. Where, again, alpha 0 is just either the data maximum or it's this starting initial point alpha 0, 0 if all the data happen to live to the left of that. Now, this is fairly tractable integral. It's just a power rule. If n were, that's right. If n were equal to 1, we'd have to use logs here because we're basically integrating x to the minus 1. So we get a log of alpha 1, log of alpha 0. For values greater than 1, we can do this integral with the power rule, and we get some nice form. Okay, I won't bother writing it out. The interesting thing about this distribution, okay, again, as before, it's just basically proportional to our data likelihood distribution, where the constant of proportionality sort of depends on the data, but doesn't depend on alpha. So that's a common feature of these uniform prior problems. It has kind of a fat tail. So basically it's just a power law restricted to the range where it can actually exist. Right? So it's got a minimum and a maximum value, but on that interval, the distribution of alpha is basically just a power law. That gives it kind of a fat tail depending on the value of n. And for small n, it kind of becomes a problem. You get a distribution that has a mean or a median or whatever estimator you want to pick that diverges to infinity the larger alpha 1 you pick. Okay, so one of the kind of interesting questions here is going to be, is this uniform prior really kind of a good ignorance prior if it ends up playing such a large role when alpha 1 goes to infinity, we get numbers that diverge to infinity? Okay, we'll come back to that when we talk about other kinds of ignorance priors and the principle of invariance and transformation groups. But anyway, assuming that you do use that ignorance prior, this is kind of only a really nicely behaved distribution for n greater than or equal to 3. Okay, so for values of n greater than 3, we have 3 samples at least. It turns out that this distribution has a nicely behaved mean and median, and in particular when you have 3, I think it works out to be that the average value of alpha converges to something like your maximum value, your maximum data value, x1, x2, x3, times 2. Okay, so basically confirming this intuitive guess that we might have made for the single sample, but actually works out to be the case for the 3 sample problem. Okay, so that's a kind of third class of examples. Again, it's just the same basic procedure as before. In each one of these examples, really the only kind of things that have determined the course of the problem are the choices we've made for the prior distributions for the parameters and whatever model we had for the data as a function of those parameters. Okay, so the same basic procedure is going to apply in any problem of parameter estimation. So just to kind of summarize those steps, so first we'll have some prior probabilities or prior distribution assignment for the parameter, okay, based on our kind of state of knowledge of it without observing the data. We'll have some model for the data likelihood or sampling distribution. Okay, that's going to be, in the case of the EARN thing, it might be the hypergeometric distribution. Here it's a uniform distribution. It might be binomial distribution for the source-detector problem, whatever it is. We'll have to figure out our total probability of the data, which is just going to basically mean taking each one of these sampling distributions that we get for particular parameter values and integrating them up over the prior distributions, so either summing or integrating over all the possible parameter values. And then finally, we put those things together and we do our Bayesian inference. Okay, Bayesian inference will give us a posterior probability assignment, okay, from which we can pick a single estimator. Okay, pick one estimator. If we want to. I mean, it's not required, but if we, for some reason, have to extract from this full distribution a single number that we think is kind of the best value, we might pick the mean, or the median, or the peak value, or some quantile, and then we might talk about the spread of the distribution, etc. So basically, just to emphasize this again, up to step 4, this is just, or up to kind of second half of step 4, this is just multiple hypothesis testing. Exactly the same way we've done it before in chapter 4, where we're thinking about a class of hypotheses that are just defined by parameters having particular values. Okay, so we have priors for those hypotheses, we have sampling distributions for a particular hypothesis. We talk about then resolving the data into each possible hypothesis, so writing it as a sum or integral over all possible hypotheses, doing that ordinary Bayesian inference to get a posterior probability assignment. And then the only thing that makes this different is that we might then extract one particular value if we had to. That's kind of a parameter estimation problem. One other thing I think that is interesting then to note about this German tank problem or taxicab problem is that if you look at the answer that we get to, our kind of final posterior probability assignment, this power law thing with this proportionality constant, it doesn't look like the data actually appears anywhere, right? So we said our data is this set of numbers, x1 through xn. Okay, we wrote out our sampling probability of the data, and we got to the point where the data kind of seemed to have disappeared. Now, actually, the only place the data actually matter here are in calculating this number alpha 0. Okay, so alpha 0 depends on the maximum of the data, and in particular whether that data maximum is to the right of our kind of initial left-hand guess for alpha. If it is, then it affects the posterior probability assignment. And what that means is that actually this data maximum is what's called a sufficient statistic for alpha, for the parameter alpha. Okay, so in essence, the only way that the data affect our estimate of alpha is through this summary statistic, which is their data maximum. Okay, there are going to be many other classes of problems where that feature holds true, where the data basically don't matter beyond some summary quantity of them for the purposes of estimating a particular parameter. And that's going to be called a sufficient statistic for that parameter. And that's what we're going to get into in the substance of chapter 8.